Let's just dive right into this, guys. Today's explainer is a visually driven journey through Chapter 4, which is all about determinants. If you've ever stared at a massive grid of numbers, a matrix, and just wondered, how on earth do I pull a single, meaningful answer out of this mess? Well, you are in the exact right place. We are going to decode the logic behind the numbers. This quote from C.P. Steinmetz perfectly captures the essence of linear algebra. He says, "All mathematical truths are relative and conditional." And honestly, that hits the nail right on the head. Our equations, our real-world models, they really only work if their underlying structure allows them to. And as we're going to see today, there's this hidden condition that dictates if a problem is even solvable at all, and it's all based on one single number.
All right, here's our roadmap for the chapter. 1. The key to linear equations. 2. Calculating the magic number. 3. Geometry, area of a triangle. 4. Minors, cofactors, and adjoints. 5. The matrix inverse. And finally 6. Solving the unsolvable.
Okay, part 1. The key to linear equations. The diagnostic key. Mathematicians like P.S. Laplace helped build this whole framework centuries ago. And they didn't do it just for kicks. They needed a way to cut through the absolute headache of unsolvable algebraic webs. When you're dealing with massive systems of linear equations, variables interacting with other variables all over the place, they needed a definitive test to see if a unique solution even existed before wasting hours trying to calculate it. So Laplace and others formalized the rules that we literally still rely on in modern engineering and science today.
So the absolutely crucial point here is that this magical number, the determinant, only exists for square matrices, meaning matrices with the exact same number of rows and columns. Think of a matrix as a complex machine. Well, the determinant is basically the diagnostic readout of that machine. It ties a single, unique, real, or complex number to the entire square matrix, and it acts as the ultimate gatekeeper for finding solutions.
Moving on to part 2. Calculating the magic number. Building the blocks. Calculating a 2x2 determinant is, honestly, as simple as a really quick cross multiplication. You take your matrix, let's say elements on the top row and elements on the bottom row. You just multiply the top left by the bottom right. Boom! Then you multiply the bottom left by the top right. Finally, you just subtract that second product from the first. That simple subtraction gives you your diagnostic number. It's fast, it's elegant, and it's incredibly powerful.
Now, when we escalate to a 3x3 matrix, don't panic. We aren't learning a whole new type of math. We're just breaking it down into those smaller second-order pieces we already know. You just pick any row or column, and since a 3x3 has 3 rows and 3 columns, there are exactly 6 different ways to expand it. You isolate an element, grab the smaller 2x2 grid that's left over, and calculate its determinant. The only trick here is keeping track of the positive and negative signs based on the element's position. But the core logic, exactly the same.
All right, part 3. Geometry, area of a triangle. So we have this abstract grid of numbers, right? But you might be wondering, how does this actually translate into measuring physical, geometric space out in the real world?
Well, it turns out this algebraic tool translates flawlessly into pure geometry. If you have the coordinates for the 3 vertices of a triangle, you might be used to that really long, tedious, messy algebraic formula on the left. But look at the right side. The determinant transforms all that into a sleek, clean, and perfectly organized grid. You literally just stack your x and y coordinates into the first 2 columns of a 3x3 matrix, fill that third column with 1s, and find the determinant. Multiply the absolute value by 1/2, and bam, you have your area. Since area always has to be positive, we just take the absolute value of all that calculation. It is such a massive visual upgrade.
And hey, fun bonus fact, if your area calculation hits exactly 0, you didn't fail. You've actually just proven that your triangle is, well, a flat line. Think about it. If the area of a triangle is 0, it means the 3 points don't form a shape at all. They are completely collinear. It's an incredibly fast way to mathematically prove that 3 points sit on the exact same line.
Okay, part 4. Minors, cofactors, and adjoints. Leveling up.
So this next sequence acts as the essential prep work we absolutely have to do before unlocking a matrix's ultimate power. It sounds like a lot of steps, but it's just a highly systematic process. First, we find the minor of an element by just deleting its row and column. Next, we apply a specific positive or negative sign based on its position to get the cofactor. We do this for every single element and build a brand new matrix entirely out of those cofactors. Finally, we transpose it, which just means flipping the rows into columns. The result is called the adjoint matrix. But wait,
If you're dealing with a simple 2x2 matrix, you can skip all that long math and use this incredibly satisfying shortcut. To find the adjoint of a 2x2, you literally just swap the positions of the elements on the main diagonal. Just switch them. Then, for the other diagonal, leave them exactly where they are, but flip their signs. And that's it. You've instantly created the adjoint matrix without calculating a single minor or cofactor. So good.
Moving on to Part 5, the matrix inverse, the ultimate diagnostic.
Here is where the determinant acts like a binary switch, telling us immediately if we can even proceed. If the determinant of your matrix is exactly 0, the matrix is what we call singular. It's a dead end. An inverse simply does not exist. However, if the determinant is literally any number other than 0, the matrix is non-singular, and you've got the green light. An inverse is entirely possible.
Without that non-zero determinant, our journey completely stops. Which actually proves Steinmetz right from our very first slide. The math is strictly conditional. Theorem 4 states this as absolute mathematical law. A square matrix is invertible if and only if it is a non-singular matrix. That one calculation we learned early on dictates the reality of the entire mathematical system.
Now, if we are clear to proceed by our diagnostic, here are the 3 sequential steps to successfully invert your square matrix. Step 1. Verify it's non-singular, meaning determinant is not 0. Step 2. Build that adjoint matrix we just talked about. And step 3. Simply divide that entire adjoint matrix by your original determinant value. Mathematically, it's 1 over the determinant multiplied by the adjoint. And just like that, you have your inverse matrix.
All right, final section, Part 6, Solving the Unsolvable, the Real-World Application.
Before we try to solve some massive system of linear equations, our determinant diagnostic tells us which of these 2 realities we are living in. A system is consistent if it has 1 or more valid solutions. It's inconsistent if absolutely no solution exists. In this explainer, we're focusing on the beautiful scenario where the determinant proves we do have a unique, singular solution ready to be found.
And this brings us to the grand finale. This is how we turn a chaotic web of equations into one clean, sweeping calculation. You just extract all your coefficients into matrix A, your variables into matrix X, and your constant answers into matrix B. As long as the determinant of A isn't 0, you find the inverse of A and multiply it by B. That single operation, x equals A inverse times B, instantly solves for every single variable in your system simultaneously. It is an absolute game changer.
So I'll leave you with this. If all these mathematical truths are completely conditional on a single underlying number, how might these invisible structural grids be secretly governing the software, the economics, or the engineering models you rely on every single day? Think about that the next time you use a 3D application or route your way through traffic using GPS. It's the silent diagnostic number running our digital and physical world. Keep looking for those hidden structures, keep testing those conditions, and we'll catch you in the next explainer.